All right, so in preparation for class tomorrow, I wanted to talk about a few things and go over a couple examples. So first is just defining gravitational and potential energy, or quantifying them. So we know that gravitational potential energy is the energy stored in an object's position, or I guess actually vertical position within a gravity field. So right there, we can see that it's going to depend on three things. So one, in order to be an object, it must depend on the mass. Two, its vertical position in a gravitational field, delta y. And then three, the strength of that gravitational field itself. Or sorry, lowercase g. And so greater masses are going to influence a gravitational or potential energy. Different heights in the field are going to influence the potential energy, as well as the field strength. So an object of the same mass and same vertical position in the gravitational field on the moon versus the Earth are going to have different results. Now, let's consider this scenario here. So let's say we have a block at the surface of the Earth, and then we start lifting it at a constant velocity. Well, in order for the block to rise at a constant velocity, we know that whatever applied force we have up must be equal to the gravitational force down. And since the gravitational force is constant, the applied forces can be constant as well. So we have some delta y, some delta y here. Now, if we were to actually create a graph of what's happening here, so let's say we have our y displacement in meters here, and we have our force in newtons, where in this case, our force is Fa, which is equal to mg, the force of gravity. So the force itself is constant as the vertical position increases. Well, typically we look at slope and area. There's no slope here, so not particularly helpful. So what about the area? Well, area is equal to base times height. So the base is the change in position, delta y, and then your height here is f. Or in this case, since f is mg, delta y. Now, very much like on our spring potential graph, here, where we had force versus spring length, we had a slope showing the K value, or how stiff or how stretchy that spring is, and that is our spring constant, and the area underneath was the elastic energy. Here, the area under a force versus delta y graph for the object that's being lifted up here, this area is actually showing us our gravitational potential energy. So this tells us that our gravitational potential energy stored in an object, a height above a reference point in a gravitational field, is mg delta y. Now, something I do want to clarify here is that this delta y is taken in reference to a point. So, for example, let's say, as I shoot this video, I am in the second floor of the STEM building. So let's say this is STEM building, and I'm up here. Let's say I have a mass of 80 kilos, and we're gonna use delta or G as 10 newtons per kilogram. So I can set where I want my reference point to be anywhere. Typically, we set our line of zero potential at the floor. And so here, if I'm in my room, I want to set my line of zero potential here. And this is just the point where we say y equals 0, and if y is equal to 0, EG has to be 0, because if EG equals mg delta y, and our y is 0 at that point, then so must the potential energy. So in the room, here, my EG is 0. Now, if I were to take myself and go outside the room and stand on the floor, let's say there's a difference of 10 meters here. So this is my starting point, and then down here would be my final point. If I were to calculate my potential energy, mg delta y, so my mass of 80, gravity of 10, and then my delta y being negative 10 meters, since I've actually gone down a height of 10 meters here. Now, this tells me that my energy is going to come out to be negative. And when we were talking about elastic energy, we talked about all energies being scalar quantities, not vector quantities. So they do not have direction. So what does this negative here mean? Well, in the case of potential energy, a negative tells you how much energy you need to restore yourself to the point of zero potential. So right now I'm in what is sometimes known as an energy well. And reference to where I set my line of zero potential, it would take 8,000 joules of energy to bring me up to this point. And positive potential energy would just tell me that I have some potential energy that's greater than 0. Negative tells me this is the amount of energy required to take me from here to my point where I would have 0 potential. And because it's proportional to EG equals mg delta y, we can see that EG is proportional to m. So if the mass increases, the potential energy increases. If the gravitational field changes, so Earth has a stronger gravity field than the moon, so on Earth you would experience more potential energy than you would on the moon. And likewise, that is proportional to that delta y. So the greater you are above wherever you have chosen to set your point of zero potential, the more energy you will have. Again, typically we use the floor. That's not a hard and fast rule. It's just typically a good recommendation. Now, kinetic energy. So kinetic energy is the energy stored in an object's motion. So that means that kinetic energy is going to depend on two things. One, in order to be an object, it must have mass. So kinetic energy is going to depend on the object's mass. The second is, in order to be in motion, it must have a velocity. So kinetic energy is going to depend on these two things here. Our equation for kinetic energy is 1/2 mv squared, very similar to our equation for spring potential energy. Now, here, kinetic energy is proportional to mass. So if I double the mass of an object, its kinetic energy doubles. However, the kinetic energy is proportional to the square of velocity, not just velocity. So here, if I double an object's velocity, its kinetic energy quadruples. So oftentimes on the AP exam, they'll give you a problem where you'll have some initial velocity, you'll be asked to find the final velocity, and then ask how that affects the kinetic energy. So for example, if you have an initial velocity of 2 meters per second, you solve the problem and you have a final velocity of 4 meters per second, and it asks, what does that change in velocity do to your kinetic energy? Well, you doubled your velocity from 2 to 4, so your kinetic energy would have to quadruple. So always keep in mind that squared relationship.